Okay, very good afternoon, one and all. In the last class, we completed module 3. Okay, so elements of PCM we completed. So in that, after completion of that, we completed uh, the basic transmission bandwidth required to transmit a PCM signal. Okay, so it is equal to half that of the signaling rate. So signaling rate is the number of bits transmitted per second, and it is equals to the product of number of bits per sample and the sampling frequency. Okay, so n into fs, we represented information rate capital R as n into fs, where fs is a sampling frequency and n is the number of bits transmitted per sample. Okay. And finally, we concluded that the transmission bandwidth required for a PCM signal is equal to half that of the signaling rate. So R by 2. So NFS by 2 you will get. But in order to avoid the aliasing problem, Fs should be greater than or equal to twice that of the message signal frequency. So please replace Fs as 2Fm. Then you can get the minimum transmission bandwidth required to transmit PCM signal as n into Fm. See, always it should be greater than or equal to n into Fm. Okay, so this is all we completed the things that in the till the last session, and in the today's session we can start the quantization error. Okay, already I told you why we need to consider the quantization noise, because we cannot be it's very difficult to eliminate. Okay, so we need to consider that quantization noise effect while evaluating the SNR for PCM system. Okay, and because we have so many encoding systems, channel encoding systems which can detect and correct the error bit locations. Okay, so and even you can correct that error data bit. So that's why we need to consider the effect of quantization noise on the SNR of PCM system. Okay, so let us move to the individual slides. See, after completion of this module, each and every student should be able to derive the expression for the quantization error as well as the signal to noise ratio for a PCM system and under uniform quantization. See, here will consider the step size as fixed while evaluating the PCM SNR for the PCM. We'll consider uniform step size or fixed step size. So that's, and already we discussed what is the meant by uniform quantization. Okay, so it is also called as linear quantization, whereby the step size for the staircase waveform is fixed. Okay, so the step size is nothing but the spacing between the representation levels or amplitude levels out of 2 power n. Okay, so next let us move to the quantizer. So what is quantizer? And every student know that quantizer converts the continuous amplitude sample signal into discrete amplitude sample. So it means that the quantizer divides the amplitude axis into 2 power n number of levels. Okay, so where n is the number of bits present per sample or per frame. And here why we are representing x of nts instead of x of t? Here x of nts represents that it is a sample signal n suffix ts. Okay, n t suffix s, it represents that the signal exists only at sampling intervals where n ranges from minus infinite to plus infinite. Here the coming to the input, the amplitude is continuous but the time is discretized. Okay, that is applied to the quantizer. Quantizer divides the amplitude axis into 2 power n number of levels. Okay, so here in the output, if you observe the output expression, it is represented as x suffix q of nts. The suffix q represents that it is the quantizer signal where we have 2 power n number of amplitude levels. Please observe the characteristics of quantizer x versus the quantizer signal. Let it be q of x. Here I am representing the output as x suffix q of nts. Okay, and if you observe the transfer characteristics of the quantizer, it is of uniform step size. Okay, because the spacing between, because the spacing between the amplitude, spacing between the each successive representation level is constant, So what is the representation level? Amplitude levels, okay, shown in the y-axis. So if you observe the spacing between each successive y-axis amplitude level shown in the y-axis, it is constant. Okay, that's why I can say that this characteristics is one of the example for uniform quantization. Okay, next thing is here in this graph especially shows that it is a mid-thread quantizer, because the origin lies in the thread position of the characteristics. Now, what is the error generated by the quantizer? If we find, for example, if we observe some deviation from the input, if we observe that the output deviates from input, then I can say that there exists some error. Okay, so what is the error then? The difference between the output of the quantizer to that of input is generally defined as the error. So here error is equal to xq of NTS minus x of NTS. What is the error shown here? It is xq of NTS minus x of NTS, where xq of NTS is a quantized signal and x of NTS is a sampled signal. Okay, so is this slide okay to everyone? Can we move to the derivation of quantization error? Okay, so error equals to xq of NTS minus x of NTS. Please keep that equation in mind. Okay, let us move to the next slide. In this slide, you can observe that the error inherited due to quantization, what we discussed from the last slide, and we represented the corresponding equation, and we took that equation as 1, okay, which is xq of NTS minus x of NTS minus x of NTS. Okay, so take that equation as 1. Now please observe the characteristics, and if you observe the characteristics, it is a mid-rise type of quantization, because in these characteristics, if you observe, the origin lies in the rising position of the staircase waveform. Here the staircase waveform is represented with blue color staircase response. Okay, so here it is a like mid-rise, because the origin lies in the rising position of staircase waveform. Now, here what the quantizer will do? Quantizer divides the amplitude axis into 2 power n number of levels. Okay, let us assume that there are let the amplitude division. Let the amplitude is divided into L number of levels, capital L, where L is 2 power n. Okay, L is the number of representation levels, which is equals to 2 power n. Okay, so n represents the number of bits per sample. Okay, please observe the graph once again. In the transfer characteristics, x-axis is the input signal. Okay, continuous amplitude, and y-axis is discrete amplitude, because the quantizer converts continuous amplitude signal into discrete amplitude sample. So x-axis is the input, which is of continuous amplitude, and y-axis is it's a discrete amplitude, where the y-axis is divided into 2 power n number of levels. We assumed it as L number of levels, and also assume that please observe the second point, and also observe that the x-axis is a continuous signal. Already we discussed, it is a continuous amplitude. Okay, so let that amplitude range from minus x max to plus x max. On the negative extremity, let the magnitude be minus x max, and the positive extremity be plus x max. Okay, now how can we define the step size? Step size is defined as the ratio between the difference between, or the total amplitude range, total continuous amplitude range to that of the number of representation levels. How can we define step size? Step size is defined as the ratio of the total continuous amplitude range, or you can say that it has the difference between the maximum to minimum amplitude range to that of L number of representation levels. But what is the minimum extremity? Minimum extremity minus minimum extremity here is minus x max. Okay, so x max minus of minus x max. So it will be 2 x max in the numerator divided by 2 power n. Okay, because how many levels into how many levels we are dividing into L number of levels. These continuous amplitude range that range from minus x max to plus x max is divided into L number of levels that is shown in the y-axis. Okay, thereby you can define the step size as total continuous ratio of total continuous amplitude range to that of the number of representation levels divided number of representation levels. So L. So it will be x max minus of minus x max divided by 2 power n. So it will be 2x maximum divided by 2 power n. Now, if the input signal, for example, if you normalize the input signal, then the maximum extremities, the maximum value is 1. Okay. So if any signal is normalized, it is normalized to a maximum value of plus or minus 1. Okay. So upon replacing the x max as 1, the equation 2 can be represented as delta equals to 2 by 2 power n. Delta equals to 2 by L, or it is also equal to 2 by 2 power n, because L equals to 2 power n. And as x max equals to 1, you can directly obtain it as 2 by L. So what is delta? Delta is the step size, which is equals to 2 by L, or 2 by 2 power n for normalized input. Okay. And one more thing that you should remember here is we are going to calculate the SNR for a PCM system under normalized input signal. Okay. So what are the assumptions? The positive extremity magnitude is equals to 1. Now, okay, I think the first equation 1 and equation 3 are now you got how to extract the error from equation 1 and 3. I think we can be able to extract the quantization error Emax. Okay. Now please all of you observe the transfer characteristics carefully, and any one of you please respond. Please carefully observe my question. I am asking you at the instant of x of NTS, at the instant of x of NTS equals to 0. So let us assume, take the instant where x of NTS is 0. Whenever the x of NTS is 0, and observe the positive staircase waveform. First, please observe the positive staircase waveform. Okay, and that staircase waveform passes through origin. First, please observe the positive staircase waveform. Whenever at x of NTS equals to 0, our output xq of NTS reaches to the staircase waveform goes to a maximum of delta by 2. So whenever x of NTS is equals to 0, xq of NTS value is delta by 2. Now at each and every instant you are known with the values of x of NTS and xq of NTS. I think you can be able to calculate the error E from the equation 1 as xq of NTS minus x of NTS. Now please tell me what is the value of error E when x of NTS equals to 0. Observe the positive staircase waveform and tell me what is the value of error when x of NTS is 0, xq of NTS output is delta by 2. What is the error then? Delta by 2 minus 0. Must C2 చెప్పండి.
Delta by 2.
Delta by 2 minus 0. So it is equals to delta by 2. Okay, good. Similarly, if you observe at the instant x of NTS equals to delta, whenever x of NTS is delta, output goes to 3 delta by 2. 3 delta by 2 minus delta, how much? How much? Any one of you?
Minus delta by 2.
3 delta by 2 minus delta ma. It is
Delta
delta by 2. Okay. So
delta
similarly,
2.
yes, it is delta by 2. Similarly, at x of NTS equals to 2 delta, output goes to 5 delta by 2. So 5 delta by 2 minus 2 delta. 5 delta by 2, 5 delta minus 4 delta by 2. Once again, it is delta by 2. So the thing that you should identify here is during the positive staircase waveform, the quantization error at any instance of input and output, the quantization error equals to plus delta by 2. And similarly, observe the negative staircase waveform. Whenever input is 0, output is minus delta by 2. So minus delta by 2 minus 0, how much? Minus delta by 2. Okay. Similarly, if you observe x of NTS as minus delta, then the output goes to minus 3 delta by 2. So what is the difference there? Error is once again minus output, that is minus 3 delta by 2 minus of minus delta. So you will get minus delta by 2. So during the negative staircase response, the error at any instance of input and output is equals to minus delta by 2. And during the positive staircase waveform, the error inherited is how much? It is plus delta by 2. So now what is the range of the error? What is the range of error from negative staircase waveform to positive staircase waveform? The range of error is from minus delta by 2 to plus delta by 2. Okay, the range is from minus delta by 2 to plus delta by 2. Now, so what is the magnitude then? The magnitude of quantization error is modulus of delta by 2, and it range from minus delta by 2 to plus delta by 2. So from this slide, you should remember 3 points. One is error definition, quantization error definition, that is output of quantizer, that is quantized signal minus sampled signal, and xq of NTS minus x of NTS. That is first point. And second point is that the definition for step size. Step size is defined as the ratio of the continuous amplitude range to that of the number of representation levels. Okay. So x max minus of minus x max divided by 2 power n. So it is equals to 2x max divided by 2 power n. Okay. So if the signal x of t is normalized, then x max equals to 1. So it is 2 by L. So you can also write it as 2 by 2 power n. Okay. So always remember here that the signal for normalized signal only we are going to calculate the SNR. So here step size definition is 2 by L only. Instead of x max, replace it as 1. So 2 by 2 power n. So what is the third point? Maximum quantization error is mod delta by 2, and the range is from minus delta by 2 to minus delta by 2, and it is plus delta by 2 for the positive extremity. Okay. Now that is the 3 points. Please let us move to the next slide. Now we are going to calculate the or represent the probability distribution function for the quantization error E. So what is the E value? E value is mod delta by 2. So mod delta by 2, it exists at minus delta by 2 to plus delta by 2. Okay. Now please observe the first graph. The first graph represents the general probability distribution function for a uniform function. Okay. Here a function exists only in between A to B, and beyond that range no signal exists. Okay, no function exists. Then we can define the magnitude of the function as 1 by b minus a. If the function has uniform distribution from a to b, then the magnitude of the particular function can be represented as 1 by b minus a. Now please apply the same thing to our quantization error. So let us, in order to get the probability distribution function of quantization error, let us take it as f suffix e of e. F suffix e of e. Okay, so what is quantization error? That range from minus delta by 2 to plus delta by 2. So because it is of uniform quantization where step size is fixed, so the magnitude is uniform. Okay, so any function, if it is uniform between the two extremities a and b, the magnitude can be represented as 1 by b minus a. So what can be the magnitude of quantization error then? What can be the magnitude of the probability distribution function of quantization error? 1 by b minus a, where b is delta by 2. Yes, and a is minus delta by 2. So it is 1 by delta by 2 minus of minus delta by 2. So how much? 2 by 2 delta. So it will be 1 by delta. Now please observe the equation here, shown here. Fx of x is a general equation. It is equals to 1 by b minus a magnitude whenever the x value lies in between a and b. Okay, but whenever the error value lies in between minus delta by 2 to plus delta by 2, the probability distribution function magnitude is 1 by delta. Okay, the probability distribution function magnitude is 1 by delta whenever the error range from minus delta by 2 to plus delta by 2. Okay, and beyond that range, that is for error less than minus delta by 2 and greater than delta by 2, what is the magnitude? Its magnitude is 0. The function only exists. The function only exists in between minus delta by 2 to plus delta by 2. Okay, beyond that, no distribution function exists for the quantization error. Is this slide okay? From this slide, we can conclude the probability distribution function of quantization error, Fe of E, which is equals to 1 by delta for the error that lies between minus delta by 2 to plus delta by 2. Beyond that range, there is no distribution function. So that's why Fe of E equals to 0. Please remember this equation. Okay, magnitude is 1 by delta whenever error lies in between minus delta by 2 to plus delta by 2. Now, let us move to the next slide. So, what is our final intention? Our final intention is to calculate the SNR, signal to noise ratio, okay, of the PCM system. What is the general definition? Signal to noise ratio is defined as the normalized signal ratio of normalized signal power to that of normalized noise power. So what is the SNR definition? Normalized signal power to normalized noise power ratio. Okay. Now, for some time, please keep the numerator section aside. Okay, first of all, let us calculate the denominator section. What is the denominator in the SNR? Normalized noise power. Normalized noise power. We can also call it as quantization noise power. Quantization noise power under normalized inputs. Okay. So quantization, because here we are considering only quantization noise into effect. Okay. So we can define noise power as quantization noise power. Now, how can we define the noise power? It's defined as the mean square value of the noise signal to that of resistance value. Okay. So how can you define noise power or quantization noise power? Noise, you can replace with the term error here. Okay. So quantization, you can call it as quantization error or quantization noise. Okay, remember. You can replace quantization error or quantization noise. Now, how can we define quantization noise power? It is defined as mean square value of the quantization error to that of a resistance value. Now, under normalization, the load resistance value is equal to 1 ohm. Okay, so I can say that quantization noise power is directly equal to mean square value of the quantization noise signal or quantized error signal. Okay, so noise power is equal to expectation of E square, because R equals to denominator R equals to 1 ohm for normalized inputs. Okay, now, so if we calculate expectation of error square, that is nothing but directly the noise power. Please remember that. So what we can conclude from this slide, we are going to calculate the signal to noise ratio. How can we define the signal to noise ratio? It is defined as the ratio of normalized signal power to normalized noise power. Okay, so let us calculate the normalized noise power first. So under normalization, R is 1 ohm. So quantization noise power is directly equal to the mean square value of the noise signal, because denominator R equals to 1 ohm. Okay, now let us calculate the expectation of error square. That is nothing but the mean square value of the quantization error. Okay, let us go to the general equation for mean square value. Okay, so expectation of x square. Let us define some general equation for the function x. Let us define the mean square value. How can we define mean square is equal to integral minus infinite to plus infinite x square into its probability distribution function. Okay, please replace the error E. Please replace x with E, because here we are evaluating the mean square value of the noise signal or error signal. Replace x with the term E. Okay, so then you can get that equation 5. So expectation of E square equals to minus infinite to plus infinite E square into its probability distribution function, that is Fe of E dE. Okay, now, so finally we got the mean square value of quantization error as expectation of E square, which is equals to integral minus infinite to plus infinite E square into Fe of E dE. But all of you please remember that the probability distribution function of quantization error exists only within the duration or within the span from minus delta by 2 to plus delta by 2, because already we calculated the quantization error range, that is from minus delta by 2 to plus delta by 2. Okay, so that's why we can replace the integration limits to minus delta by 2 to plus delta by 2. Within the duration, what is the value of Fe of E? Any one of you please respond. Within the limits from minus delta by 2 to plus delta by 2, what is the probability distribution function of quantization error?
1 by delta.
1 by delta. We calculated it as 1 by delta. So please replace Fe of E as 1 by delta and the limits, integration limits as minus delta by 2 to plus delta by 2. Okay. Let us calculate the mean square value of the quantization noise first. Let us move to the next slide. Now, so in this slide you can observe the same old definition which we have seen earlier. The probability distribution function of quantization noise is defined as Fe of E equals to 0 beyond the limits from minus delta by 2 to plus delta by 2, and within the limit it is equals to 1 by delta. So take the integration within the limit from minus delta by 2 to plus delta by 2. Please substitute the error function Fe of E from equation 6 in the mean square value equation. You will get expectation of E square equals to limits we changed it as minus delta by 2 to plus delta by 2. E square into 1 by delta into dE. Now, 1 by delta is you can take outside the integration because it is constant. It is independent of that E function. So take that outside the integration. Okay. So now you will get integral E square dE. What is the integration of E square dE? Let us simplify this. What is the integration of E square dE? X square dx. Take 1 by delta outside the integration. And what is the integration of x square dx?
X cube by 3, ma'am.
X cube by 3. So please replace x with e. So you will get e cube by 3. Please observe the next slide. Expectation of error square equals to integral minus infinite to plus infinite e square into 1 by delta dE. Okay. So take 1 by delta outside the integration and integral in minus delta by 2 to plus delta by 2 e square dE is equal to e cube by 3. That range from minus delta by 2 to plus delta by 2. Please substitute the values of the limits. That's from delta by 2 and minus delta by 2. So you will get 1 by delta. Observe the second step. 1 by delta and we took 1 by delta as common. So you will get substitute delta by 2. So delta by 2 whole cube by 3 minus of minus because here we have cube. Okay, so minus cube, minus delta whole cube, you will get minus delta cube only. So minus of minus you will get plus delta by 2 whole cube divided by 3. Now, observe third step, it is equals to 1 by 3 delta because take 3 as 3 outside the brackets. So you will get take 3 common. So 1 by 3 delta in the denominator into delta cube by 8 plus delta cube by 8. So within the brackets, the summation will be 2 delta cube by 8. So it will be delta cube by 4. Delta cube by 4. So we have delta cube in the numerator and delta in the denominator. So you will get delta square in the numerator and 4 into 3 you will get 12. So finally, what is the mean square value of the quantization error? You got expectation of error square as delta square by 12. So this is very important for your examination. Derive the expression for quantization noise power and term. Quantization noise power is generally defined as the mean square value of the ratio of mean square value of the quantization error to that of normalized resistance. So R equals to 1 ohm. So expectation of error square is nothing but the quantization noise power. So how much? Quantization noise power is equals to expectation of error square is equals to delta square by 12. This is all for a PCM system only. For delta modulation, it is delta square by 3 you will get. Okay, we can derive it in the next to the modules. So what is the mean square value of quantization error? Delta square by 12. But what is delta? Recollect from equation 2. What is delta? 2 by L or 2 x max by L. Whenever x max equals to 1, it is 2 by L, where L is the number of representation levels shown in the y-axis or amplitude axis. So it will be 2 by 2 power n. Okay, let us move to the next slide for simplification. So already we defined that quantization noise power is defined as the ratio of mean square value of the quantization error to that of load resistance, So n equals to expectation of error square divided by R. For normalized input, R equals to 1 ohm. So n will be how much? Directly equals to expectation of error square. So it is equals to delta square by 12. Now what is the quantization noise power for a PCM system? What is the quantization noise power for a PCM system? Any one of you respond? What is the quantization noise power for the PCM system?
Delta square by 12, ma'am.
Delta square by 12. What is delta? Delta is the step size.
Step size, ma'am.
Yes, it is equals to 2 by L or 2 by 2 power n. Okay. Now please replace, observe the seventh equation. So that seventh equation represents the quantization noise power. Seventh equation represents the quantization noise power, which is nothing but the denominator section of SNR. So finally we derived the denominator part. Okay. Now all of you please replace delta. We defined delta as the ratio of 2x max to 2 power n. Already we defined it as 2 by L ani manam derive chesamu. Okay. Please substitute the value of delta as 2x max by 2 power n, or directly take x max as 1, no problem. So you will get 2 by 2 power n whole square divided by 12. 2 by 2 power n whole square divided by 12. Just we replace the value of step size as 2 by 2 power n, taking x max as 1. Now here also, here actually I have derived the generalized equation first. Okay, so what we are doing here, instead of taking x max as 1, for some time please don't take x max as 1. First let us derive the generalized equation, and then under normalization you can take x max as 1. Okay, now let us assume the normalized signal power as P. So what is the definition for normalized signal power? It is defined as the ratio of mean square value of the signal to that of normalized resistance. Okay, normalized resistance is 1 ohm. If the signal x of t is normalized, then we can take 1 ohm. Okay, so anyhow, let us assume the signal power as capital P. So what is our assumption here? Let us assume this normalized signal power, that is the numerator of SNR, as capital P. So how can you write SNR? It is defined as the ratio of P, which is the normalized signal power, to that of N, where N is the normalized noise power. Okay, so already we derived N value. So P by delta square by 12, because quantization noise power is directly equal to expectation of error square. So delta square by 12 you will get. Okay, so it is equals to P by, please substitute delta as 2x max by L or 2 power n whole square divided by 12. Okay, now here in the denominator you have 2x max by 2 power n whole square actually. So 2 square 4 by 12 you have. Okay, so that is 4 by 12, you will get 3. So you will get it in the numerator, because denominator by denominator, you take that 3 to the numerator. So 3p into, once again this 2 power n is also under denominator, so that also will go to the numerator. So 2 power 2n you will get, divided by x max square. Okay, divided by x square maximum value. So what is the generalized equation for SNR? SNR equals to 3pl square by x square maximum value. Okay, where x max is the positive extremity. What is L? L equals to 2 power n is the quantized value. L equals to 2 power n. Now here we did the simplification. So please remember this generalized equation. Sometimes in exams you need to derive the generalized equation by assuming the signal power as capital P. SNR equals to 3pl square by x square max. Okay, now if the input signal x of NTS is normalized, you can assume x max as 1. So directly SNR will be 3p L square, where L equals to 2 power n. So you will get 3p into 2 power 2n. So what is the SNR value? What is the SNR for quantized PCM, uniform quantized PCM signal? 3p into L square divided by x square maximum. When x max equals to 1 under normalized input, it is equals to 3pl square. where L equals to 2 power n. L is the number of amplitude levels or number of representation levels, which is equals to 2 power n, where n is the number of bits per sample. Okay. So please observe the SNR expression. It is equals to 3p L square by x square maximum value or x max square anachu directly. So in general, if for the normalized input signal, the destination signal power P is always less than or equal to 1. So P is always less than or equal to 1 for normalized input. Okay. So SNR is less than or equal to 3L square because P is less than or equal to 1. So SNR will be less than or equal to 3L square. The maximum value is 3L square. So it is always less than or equal to 3L square for normalized input. Now, so finally, up to this, what we concluded? We concluded the quantization noise power and we got that as delta square by 12, where delta is 2x max by L. Okay, where L is 2 power n. L is the number of representation levels. So upon substituting the value of n as delta square by 12 in the denominator, you can get SNR as 3p L square by x max square, where p is the assumed normalized signal power, which can be obtained by taking the ratio of mean square value of the signal to the resistance value. Okay. So finally, if you assume x max as 1 for normalized input, you will get it as 3p L square. Okay. In general, the destination signal power P is always less than or equal to 1 under normalized inputs. Okay. So what is the maximum value of SNR? 3L square, and it is always less than or equal to 3L square for normalized input. Okay. Let us move to the next slide. Let us calculate the, so what is the first, please observe the first point in this slide. It is SNR equals to 3L square. So it is always less than or equal to 3L square because P value is less than or equal to 1. P value is less than or equal to 1. Okay. Now, so SNR, if you want it in decibels, if you want the SNR in decibels, it is equals to 10 log SNR base 10, but SNR is how much? 3L square or 3 into 2 power 2n, because L is 2 power n, so L square will be 2 power 2n. So in the second point, we are going to obtain the SNR in decibels. So it is 10 log SNR base 10, normal value of SNR. So normal value is, it is less than or equal to 3 into 2 power 2n. Okay, please substitute that value inside the logarithm. So you will get 10 log. So it is in the form of log of AB, A into B. So you will get it as log A plus log B. So split the log AB into log A plus log B. Then 10 log 3 base 10 plus 10 log 2 power 2n base 10. Now log 3 multiplied by 10, log 3 value is 0.477, something like that. If it is multiplied by 10, you will get 4.77 plus log 2 power 2n, actually take that, okay, so you will get, okay, so you will get 2 power 2n, take this 2n outside because it is in the form of log x power y, so you can represent it as y log x. So take 2 power 2n outside the logarithm. So take 2 power that power 2n outside the logarithm. So you will get 20n log 2. Okay, so that 20 log 2 is nothing but 6.02. So finally you will get the SNR as always less than or equal to 4.77 plus 6.02 n for normalized input and normalized error. Okay, So what is the maximum value of maximum value of SNR? 4.8 plus 6n, and it is always less than or equal to that particular value for normalized inputs. Okay, so like this type of questions you will get in objective examination. Okay, so SNR in decibels is less than or equal to 4.8 plus 6.02n, that is in decibels. Okay, and in normal values it is less than or equal to 3L square, or it is equals to 3PL square, where P is the signal power. For normalized signal power, P is less than or equal to 1. So SNR is less than or equal to 3 into 2 power 2n. So in decibels, it is it is less than or equal to 4.8 plus 6n. Okay, so what is the final expression for SNR? For uniform quantized PCM signal, 4.8 plus 6n decibels. This is all for normalized input x of t and normalized signal power p. Okay, is this derivation okay to everyone? At least one of you respond. Signal to noise ratio derivation for uniform quantized PCM signal.
Yes, ma'am.
Okay, ma, thank you. So like this type of questions you will get. Please go through this question. In PCM system, given full sinusoidal modulating signals, m of t is given to you. Okay, in the first first bit, you are supposed to calculate the SNR, generalized SNR expression. Already you know that it is generalized expression you need to calculate. Okay, so 10 log SNR mean that you are going to calculate the SNR in decibels for this type of m of t expression. Okay, and next you are given with L value, different values of L. Okay, and you are supposed to calculate the SNR. Okay, this type of problems we can see in the next class. Okay, I will stop the session here. So the conclusion, only two conclusion points from this session. One is the quantization noise power, which is equal of PCM system, which is equals to delta square by 12. Okay, and the SNR in decibels, it is equals to, it is less than or equal to how much? 4.8 plus 6n, and the normal values it is 3PL square, where P is the signal power. So whenever some message signal is given to you, calculate the signal power, and evaluate the SNR. Okay, anyhow we can discuss the problems in the next class, and then we can go to the module 5, that is compounding. So any doubts in the today's session? Okay, in the next class we can continue with the problems. So any doubts in the today's session?
Ma'am,
Amma, cheppandi.